Hello there, I'm Thomas Hatsios, I'm an American pilot flying the Boeing 787-900 tonight's flight. We're gonna be overflying Zurich, Switzerland, Germany, then coming back to the Zurich International Airport, the runway 14 for an Lszh localizer landing surrounding the cockpit for the pre-takeoff preparation of the quality wings Boeing 787-900 in Microsoft Flight Simulator X. I'm gonna start showing you the cockpit instruments, the displays and the functions of the Boeing 787-900 aircraft. I'm going to start with the primary flight display that displays the airspeed indicator, the airspeed selected from the pilot and flight director system panel, the ground speed, the radio altitude above the ground level, the barometric altitude above the sea level, the target altitude selected from the autopilot and flight director system panel, the ground speed, the radio altitude above the ground level, the vertical rate of climbing of the aircraft 1000 to 1000 feet per minute, of the steepness of the chronometric angles in decrease and decline in the sun. We have also the altitude indicator with the artificial horizon, the pitch lateral decrease and the back angle in decrease. We can use the Lszh localizer, the horizontal localizer and the vertical glide slope from the radio frequency antennas that transmit from the threshold runways we use for takeoff and for landing. The antennas that transmit the radio frequency of the Lszh system, the instrument landing system of the airport runway. So we have a unique frequency, radio frequency for this runway we use for takeoff and for landing. And we have the onboard antennas of the aircraft that are received at radio frequency displays the horizontal localizer and the vertical glide slope. We can see the display in the primary flight display when we are configured for takeoff and for landing. So we have also the Lszh localizer crossbars. We have the flight director crossbars for manual guidance of the aircraft and the autopilot crossbars for automatic guidance of the aircraft. We have also the angle of attack of the aircraft as it flies and the flight mode and on zero with the autopilot and the auto throttle later on vertical navigation modes. We have also you can see the HSI that displays the horizontal situation indicator, the magnetic heading and track, also the integrated display of the flight plan. So we're gonna create a flight plan using the flight management computer. I'm gonna show you later in a couple of minutes how we're gonna make a flight plan, and we're gonna input all the data of the aircraft for this flight. So we're gonna use So we're gonna use all the data of the aircraft that we need for this flight. I'm gonna show you how create the flight plan, and also you can see here I'm gonna show you the data of the primary flight display over here, the flight mode annunciator and the HSI, and also the horizontal and vertical profile of the navigation display. So we have also the navigation display that displays the horizontal and vertical profile of the aircraft as it flies. You can see the terrain and weather reflections from the weather radar, the red, green and amber or yellow indication, the terrain elevation and the distance range in nautical miles you can set, so you can predict the terrain around you, and also vertically using the vertical display indicator. We have also the terrain map, the terrain and also the water. You can see the lakes, rivers and the sea with cyan color. We have also the airport names. It's airport with a 4-letter name. So we have our own airport, the Lszh. It's in Switzerland. You can see the runways and the taxiways, the runway we're gonna use for takeoff, the runway length and its heading. Also we can see the other airports around us. You can see also the VOR station, the ADFs, the NDBs, which are the navigation aids, the nav aids. Also we have the display of the waypoints which are horizontal and vertical navigation fixes, and altitude and airspeed constraints. We have to fly through some waypoints during the flight. We can select from the flight management computer in the pre-flight phase. When I'm creating the flight plan, I'm going to show you in a couple of minutes. So also in the navigation display we can see other aircraft that fly around our own aircraft using the transponder. There is an ADC transmitter receiver that transmits our frequency to other aircraft and the air traffic control and receives from other aircraft. We can display, it can calculate from its computers the other aircraft distance and location, altitude difference from our aircraft, how many feet, hundreds or thousands of feet are above or below us, also whether the climb or the sun with respect to our aircraft. Also you can display the other aircraft. I can calculate the velocity closing in between our aircraft and the other aircraft. It will give us a warning. We have a recovery condition from the TICA system, the traffic collision and advisory system of the aircraft. Also, you can see other things. We're gonna see the autopilot flight director system panel, the ACAS, the engine indication and control system display, the flight management computer, the thrust levers. So I'm gonna start showing you all the things that we need to know before going into this flight. I'm gonna make an engine start demonstration also. After I'm gonna show you all the systems, and then we're gonna make a complete flight from takeoff, climb, cruise, descent, approach, and landing in the end part of the video. So stay with me until the end part of the video to see the complete flight. So you can see we have we can climb and descend using I'm using the side stick to control the deflection of the yoke inside the Boeing aircraft. You can see the side stick deflection is proportional to the yoke deflection. So this is the flight controls part. Also the rudder pedals. Over here we can use for the vertical rudder, the rudder pedals, the control wheel for the ailerons and the spoilers, the rolling axis, and the elevator like this, which is for climb descent. Also we have the thrust levers. Over here you can use the thrust, you can move the thrust levers forward and aft. So I'm gonna start, you can see the indication of the engines over here, the left and the right engine. I'll explain you also this function. So we'll start showing you over here the displays. So you can see the primary flight display. We have the airspeed indicated here. The airspeed, you'll see the airspeed increase when we go for takeoff and for flying. You can see the airspeed selected from the autopilot flight director system panel with purple magenta color. Also the radio altitude above the ground level can count up to 2,500 feet above the ground, the radio signal from the onboard antennas. Also we have the barometric altitude above the sea level is 1,430 feet right here, this needle line. So for the barometric pressure altitude, we use the outside pressure of the outside atmosphere, 29.92 inches of mercury over here, and also the radio altitude 200 feet, so 29.92 inches of mercury over here. You set inches of mercury hectopascals, and this will set the barometric pressure and the altitude of the aircraft from the pitot dynamic and pitot static. For the airspeed, the dynamic, and the static for the barometric altitude. So this is adjusted by the air data computer. You can see here we have heading reference and also the IRS reference system. This controls the coordinates of the aircraft, GPS receivers, the GPS receivers, the coordinates, the magnetic North Pole, a geographic North Pole, and magnetic variation depending on where we are in the world. So we have the magnetic North Pole and geographic North Pole also, and the magnetic variation display in the navigation display. This is controlled also from the air data computer, as well as the airspeed data. And also this calculates the rate of climb descent, the pitch angle of the aircraft, the laser gyroscopes for the inertial acceleration and deceleration of the aircraft, and other data. So we have also over here you can see in the primary flight display. So we have the airspeed tape, the altitude tape, the VSI, the vertical speed indicator, the altitude indicator, the pitch ladder over here in degrees, the bank angle. Also you can see how many degrees we bangle, like 5, 10, 15, 25, 30, 45 degrees. So you can see the limits, left and right turns. And also here the pitch ladder, you can see 2.5, 5, 7.5, 10, 2.5, 12.5, 15, 17.5, 20 degrees for pitch up or pitch down. And we have to pay attention to the vertical speed indicator. Even if we have a positive altitude, the aircraft might be falling down, so we need to apply thrust and do other things. So you see also, as I told you, you can see the count here is 500, 1000, 1500, 2000, like 3000, 6000 feet, for climb descent. You will see this needle moving up when we climb and moving down when we descend. So you see the setting here again, 200 knots selected, 200 nautical miles, so 360 kilometers and 10,000 feet, and the heading over here 360 degrees from the HSI. The same ones are selected from the autopilot. Flight director system panel over here. You can see the airspeed guidance of the autopilot. We select the airspeed nautical miles or Mach, the heading and the bank angle, the vertical speed, and the altitude selected over here. So the vertical speed also has the flight path angle, you will see later. So we have over here, you can see the autopilot engage and disengage switch. The airspeed select, we can set the airspeed and press the button. Also for the heading and the altitude, press the button and we'll select the VNAV mode. So we have the LNAV and VNAV function. The flight level change, climb continues, auto throttle, flight director on and off, and autopilot engage, disengage, auto throttle, left and right engage and disengage, arm and disarm, heading, bank angle and hold over here, vertical speed, roll localizer approach, and the hold for the altitude. Also you can see the other side displays are the same things. Also we have here you can see the systems display, we will see later, system CDU info, checklist, communication, navigation display, ECAS, engines and console. Left and right we can set the engines indication and the other systems either in the left or the right multifunction display, or have an extended map view as you can see. Also we set here, as I told you, the barometric altitude in inches of mercury or hectopascals. We have 29.92 inches of mercury for the barometric. Pressure altitude 29.92 inches of mercury over here. We can set also 1013 hectopascals either left or right. The range of the map, the plan menu and the menus, radio, weather radar, traffic and terrain on the display, except cancel, reject over here. We have some other indications. So you can see the horizontal profile, the distance map, the magnetic north pole heading 322, and the range right now is 18 nautical miles over here. You can see the Germany here, the France, I will show you later, the Switzerland. So you can see the terrain also. As we fly vertically, you're gonna see how many thousand feet gonna be flying when we gonna be airborne. So we have also other things like the engines indication over here, left and right engine, N1, low speed starters, low pressure compressor, and turbofan, which is engine, exhaust gas temperature per engine, left and right, N2, which is the high speed starters, high pressure compressor, turbofan, the turbofan, which is engine, fuel flow, principal, 1000 kilograms, thousands of pounds, oil pressure, oil temperature, oil quantity, and the vibration of the N2 stage of the engine. So all these are the engines indications. We have the GMX turbofan engines installed on Boeing 787-900 aircraft. So we have in each engine contains a gearbox with the FADEX. The FADEX are the full authority. This is electronic control computers. One installed per engine gearbox. Fuel tunnel redundancy. One tunnel fails, the other takes over. Controls, monitors, and displays all the engine data. You see in the left and the right engine, like the N1, which is the low speed starters, low pressure compressor, and turbine of the turbofan, which is the engine. The exhaust gas temperature per engine, the N2, which is the high speed starters, the high pressure compressor, and turbine of the turbofan, which is the engine, the high speed starter, and spool and stuff. Also we have the fuel flow per engine per 1000 kilograms to 1000 pounds, oil pressure, oil temperature, oil quantity, and the vibration of the N2 stage of the engine. The FADEX also control and monitor other things like the fuel metering unit, the outflow air pressurizer from the 5th and 9th stage of the low and high pressure compressor turbines and compressors, and also from the bypasser. We have bleed air pressurizer, which is supplied for systems like you can see here, the cabin pressurization, cabin altitude. So this is the pressurization of the aircraft over here. When we fly, we can set, you can see the bleed air pressurizer is actually coming from here, from the left and right packs from the engines. supplies cabin pressurization over here, wing and edging the ice, air conditioning, ventilation, and also the oxygen regulation in the cockpit and the cabin, and also the cabin pressurization, and also the hydraulic fluid tanks over here. So we have the hydraulic fluids are pressurized with air from the engines, or we have as a backup also the rammer turbine, the APU. We can use the APU, the small auxiliary power unit you will see in the end part of the video. To start the engines, it will provide us pressurizer, and also it can be used as a backup in flight to provide pressurizer for systems like hydraulic fluid tanks. And you can see cabin altitude right now is 1,400 feet. The outflow valves when we climb descend for pressurizing, and the pressurizing the aircraft cabin and cockpit forward and aft. 1,400 feet, we're gonna climb like 45,000 feet. The cabin altitude should be reaching like 6, 7 or 8,000 feet, and the differential pressure will be like 7.8 or 8 psi. The rate of climb descent here and the landing altitude. So this is for the cabin pressurization system. I'm gonna show you also and the engines function. I'm gonna show you also a couple more things. Also, as we climb into higher altitudes, the engines, as we climb higher, the aircraft, the pressure of the air, the density of the air, pressure, density, oxygen, become less than half than that of the sea level. We're gonna be climbing to 35, like 20, 30, 40,000 feet above the sea level, like 9,000, 10,000, 11,000, 12,000 meters above the sea level. We're gonna be having half the pressure and the oxygen and the density of the sea level. We're gonna be flying also the aircraft in an airspeed rate like 2 or 3 times faster than that of the sea level. We're gonna be having higher intake of airflow from the front fans of the engines. So we're gonna be having a different fuel air mixer just request every second. This is adjusted by the Farex, the fuel air mixer, the fuel metering unit, the fuel flow to the engines. As we use the thrust levers here to command the engine's thrust. So we have also, as we climb higher, we have freezing temperature like -30, -40, -50, -60 degrees below Celsius 0. So we're gonna be having the fuel is gonna freeze in flight. So we recirculate automatically the fuel from the wing tanks, the left and the right wing tank and the center tank, automatically from the Farex control. The fuel authority is electronic control computers running for operating variables. So they do also other things. Also, as we descend, we need a different fuel mixer. Also, they recirculate the fuel from the fuel tanks, the left and the right wing and the center tank, into the engine components to heat up the fuel from the engine's heat, and also duct heat from the engines. And also we do the same for the oil and the lubricant, right? So we have many sensors from the Farex. So this is a small explanation about the Farex control. I will show you now the flight controls over here. How I'm gonna using the flight controls to control the aircraft in flight. I'm using this side stick, the Lszh Stream 3D. That is identical to the Airbus side stick, so I can control the function of the aircraft in flight, the directional control. So we have also the outside view of the aircraft. I will talk to you about the Newton's physics, aeronautical and aerospace engineering, derive some principles we need to know for the aircraft when we fly, but the aerodynamics and the forces of flight for the air transfer pilot license, and also for the commercial pilot license. So you will see now what I mean. I will talk to you about Newton's physics, aerodynamics. So you can see the outside view of the aircraft. You can see the wings of the aircraft hold the weight of the aircraft mainly as we fly. We have also the thrust, the Z plus from the engines when we fly to propulse the aircraft, these vectors from physics that move the aircraft forward. So you can see the Z plus from the exhaust cones of the engines over here. We have also the compressor, the turbine in its engine, and the front fans, combustion chamber. You can see also here you can see we have the aerodynamic chord position, the Mach, which is 23% for this aircraft, and these wings of the aerodynamic chord is where the maximum aerodynamic lift occurs in the flight, and also the position where the center of pressure is moving forward and aft over the wings, also where the airflow becomes detached from the top surface of the wings when we fly, and the aircraft wings stall. So we need to pay attention over here from inside the cockpit to monitor from the primary flight display. We have the airspeed indicated here, so you can see the airspeed indicated, the airspeed tape, and also we're gonna be having the stall speed indicated with yellow and amber and red indication down here when flight. So we need to apply more thrust and pitch the aircraft down a little bit if we have a stall, and also avoid the angle of stall in flight. So we have also we have all these things over here. We have the center of gravity, we have the fuel tank, the center fuel tank, and the left wing and the right wing's fuel tank, where the center of gravity is located pretty much here is where the yawing axis of the aircraft is located. We can turn the aircraft left and right using the rudder in flight. So we have directional control over here, as you can see, through the center of gravity axis, the vertical axis. Also we have the nose wheel steering. You can see the nose wheels over here. So we have also directional control in the ground, like 76 degrees left and right alongside with the rudder in the ground from an initial airspeed of 0 knots, like 45 knots. We have 76 degrees either left and right deflection using the rudder pedals over here, as you can see. So we have the rudder pedals over here. As you can see, we can move the nose wheel 76 degrees, also using the tiller from 0 to 45 knots. Then it decreases because we have the rudder, the vertical stabilizer from the rudder pedals over here, the rudder. So it becomes active from 45 knots aerodynamically, and increases as we increase the airspeed. So the tiller and the nose wheel is decreasing from 76 degrees from 45 knots when the rudder is coming in to 7.6 degrees all the way up to 70 or 80 knots. It deactivates. So we have only the rudder above 80 knots for directional control of the aircraft in takeoff and landing, also in the air. So this is the control principle for the nose wheel steering for the front wheels over here, and also the rudder, which acts through the center of gravity, the yawing axis of the aircraft. So also we have this axis is from wingtip to wingtip, which is the lateral axis is the pitch axis. We use in the Airbus the side stick deflection for climb descent, back and forth. You can see the tail is moving up and down the elevator of the aircraft, so you can climb this. And you can see also the vertical stabilizer, the yaw. So we have control for flight controls if we need simultaneously. So you can see the control, the side stick over here, control for climb descent like this. So we control over here. This is the elevator control, the control column in the Boeing aircraft. The yoke of the Boeing aircraft is the side stick. In the Airbus aircraft is the same function. Also the rudder pedals, same function, no difference. So you climb and descend like this using the pitch axis. So also we have one more axis from nose to tail, transverses all the other axes. Is the longitudinal axis, is the side stick left and right in the Airbus side, in the Airbus aircraft. So you use the ailerons and spoilers and flaperons in the Boeing or in the Airbus, the ailerons and the spoilers. So this is the lateral, the roll control, the longitudinal axis of the aircraft. So you can see we make left and right thrust deflection, and we move ailerons and spoilers like this through the longitudinal axis of the aircraft. So this is the roll control, the longitudinal axis or aileron spoilers is the control wheel as you can see in the Boeing aircraft, is the side stick left and right. So we have the pitch axis, the elevator of the aircraft, control wheel, ailerons, spoilers and flaperons, and the rudder, the going axis, rudder pedal, nose wheel steering the ground, and also the toe brakes of the rudder pedals. We have also other secondary flight controls. I'm gonna show you later the flaps, speed brakes. Also we have the horizontal trim stabilizer here. I'm gonna show you how to trim the horizontal tail of the aircraft. So this is all the axis. I'm gonna talk to you also the wings. You can see here the bottom surface is more flat using the Bernoulli theory fluids. Also we have the flaps extended, so as we accelerate for takeoff, we're gonna have an angle of attack that is gonna be positive mainly on new flights. So using the Bernoulli theory fluid, the airflow is moving slower below the wings, which pressurizes the aircraft wings up into the air when we reach like 140 knots for takeoff, like 250 kilometers an hour. So also you can see so we have higher pressure below the wings. We have differential pressure between the bottom and top surface of the wings. You see the top surface of the wings is more curved, so the airflow is moving much faster above the wings using the Bernoulli theory fluid, which creates a lower air pressure, which sucks the aircraft wings and weight up into the air. So this is the aerodynamics of the aircraft that we need to know. Also, I'm gonna show you a little bit more the flight controls. Also the horizontal trim stabilizer over here. So this is a fly-by-wire aircraft. We have the fly-by-wire aircraft. We have the auto trim and the fly-by-wire channels, the normal, the alternate and the direct low of flying. Like in the Airbus aircraft, we have G limitation, acceleration of gravity for left and right turns, and climb deflects the flight controls proportionally, like in the Airbus. For instance, we have 2.5 G's left and right turns, and so you can see the primary flight control computers over here should be in the auto position. As I told you, it's next to the air data computer above the electrical, and we have also flight control surfaces. So in the Airbus you can make turns like 2.5 G left and right turn and 67 degrees maximum using the side stick, and also you can climb like 30 degrees and descend minus 15 degrees, and we'll have like climb like 1.5 G and descend minus half G. So in the Boeing it's like identical to the Airbus flight control fly-by-wire system. For the Boeing 787, maybe different limits for flying. So you can see we have the fly-by-wire system, flight control computers here. So we have the inputs for the horizontal trim stabilizer over here. You can see the control wheel. It reads horizontal elevator trim, left click down, right click up over here. So this is the horizontal tail trim switch over here, as you can see. So you can trim the horizontal tail elevator, trim, left click down, right click. So this is what it's doing. You move the elevator up and down, you trim it in flight. So when you fly climb descent, you have also the trim switch over here for climb and descent to balance the aircraft and relieve the aerodynamic pressures and effects. So you can see we have also the rudder trim. So this is the elevator trim switch, left click down and right click. So this way you trim the elevator up, you pitch the nose of the aircraft up. As you find this way you trim the elevator down, so you pitch the nose of the aircraft down as you fly. So you have the elevator trim. We have the head up declutter over here switch, and the autopilot disconnect. As you can see, disengage switch. So mainly this trim when flying manually. This way you pitch the nose up, and this way you pitch the nose down. You have also the flaps limits over here. So this is the control wheel function. Some switches we have. Also here we have the alternate Over here you can see pitch stream, alternate pitch stream over here. So this way you pitch the nose up as you fly. This is the alternate channel, and this way you pitch the nose down. So you trim the elevator again. This is the elevator control in the tail of the aircraft again. So you trim the elevator up and you trim the elevator down as you fly. You see elevator elevator trim, left click down, right click up. So we have also other things like the parking brakes over here. You can see. So we can see here how many degrees we deflect the elevator as we fly. Nose down, nose up. Right now it's 4.5. It's set probably automatically from the auto trim system. Stabilizer, nose down, nose up. Rudder trim also, the flaps position. So we're gonna be having also, as I'm telling you, we have the flight control computer. So we also use normal and alternate. If we have the auto trim system, we have a failure of the hydraulic system here that affects either the left or right horizontal stabilizer. We can lose the auto trim function from the auto panel flight director system panel, and the auto throttle, and also from the flight management computer inputs for the flight control computer's inputs. So we're gonna have come down here. This is for all Boeing 737, 747, 757, 767, Boeing 777 and Boeing 787 aircraft, for Boeing aircraft nearly. So you open from normal to cut off the stabilizer trim if you have a failure, so it disconnects the automatic trim function from the aircraft flight control computers when you have the autopilot engaged, for instance, with the flight director and the auto phone. So you're gonna have only the manual trim switch over here, pitch trim manual over here, elevator up and elevator down. I pitch the nose up and pitch the nose down like this, or in the control wheel using this channel over here. So you see again elevator up and nose up and trim down and nose down. So you balance the aircraft like this in flight. I'm gonna show you also the other side of the flight controls. Also we're gonna make you're gonna use the flight management computer in a couple of minutes to create a flight plan. So I'm gonna show you also this view of the flight controls of the side stick and the flight controls. I'm gonna show you a couple of views, more nice views of the flight control system. So you're gonna see in a couple of minutes also how we're gonna make the flight plan. So we almost finished with the systems of the aircraft. So I'm gonna show you now. You can see we have the side stick here. So I'm using the side stick to control the aircraft. So we can climb and we can descend like this. So climb and descend, make turns to the left, make turns to the right. So you can see the side stick deflection is proportional to the yoke deflection. Also the captain and the first officer control are moving together. They're interconnected in flight. Unless you have a failure, you can override one side. So you can see the side stick deflection is proportional to the yoke deflection of flight controls. Also this side view, hope you like it. You can see also the thrust levers that we have here. You can move the thrust levers forward or aft like this. so we can climb and we can descend with the elevator for climb and descend. Also you can see we have an incoming aircraft flying over here. You're gonna see it. A Boeing 737, so you can see again the side stick deflection we use over here. So climb, descend, make turns to the left, make turns to the right, use the thrust levers over here also. See the thrust commanded and the horizontal trim stabilizer, so we have full flight control. We have also in the Airbus you have the side stick priority. You can use either side stick, not like the Airbus you have either connected flight controls all the time between the captain and the first officer. And also see a little bit over here the outside view. So we make turns left, right, flight controls, rather input. So this is all flight controls we need to use for flying the aircraft. You're gonna see them also in the flight in a couple of minutes. Like this, spoilers deflected like this. So we're going for flight now for the rest of the systems. This is enough for the flight controls lesson right now. So we're gonna see now the flight management computer. So I will input all the data of this aircraft for this flight, and includes the takeoff, gross weight, the empty weight class, the passenger class, the cargo class, the fuel on board. With the fuel is stored in the left and the right wing in the center tank. We have 30% fuel in the left and the right wing tanks and 10% in the center tank. The flight management computer is going to calculate automatically the center of gravity of the aircraft from takeoff, climb, cruises, and approach and landing with burn fuel. So the center of gravity is shifted and it's recalculated every second in flight from the flight management computer. Also for takeoff, we have the minimum aerodynamic chord position, 23%, the Mach or the maximum aerodynamic lift, and also we can see the stall speed. Using this also calculates using the center of gravity and the horizontal trim stabilizer position for takeoff 4.35 degrees. It's going to be set automatically from the flight management computer. Also going to use 15 degrees of flaps for takeoff for this runway, the runway 14 in Zurich International Airport, Lszh in Switzerland. So we're going to be having the runway length, the runway slope, the wind direction and speed, the barometric pressure, the density of the air, the diameter of the air is going to give us I'm going to use maximum takeoff thrust of 99 to 100% from the engines, and we're going to be having 9 degrees on the of pitch altitude for takeoff with 15 degrees of flaps. It's going to give us the takeoff phase V1, V2 and V2 like 130, 140 knots. Now we're going to be having also the insert from the flight management computer, the seats are the side are usually departure waypoints and fixes that include horizontal vertical navigation fixes and all the airspeed constraints for the initial climb of the aircraft. We're going to be climbing to like 35, 36, 37, 39, 39, 30 1,000 feet above the sea level. We're going to be cross through some waypoints and make some turns. We're going to descend back to the elevation of the airport like 7,000 or 6,000 feet above the sea level, and we're going to be aligned with the magnetic north pole heading of 136 degrees of the runway 14 in Zurich International Airport, aligned for approach and landing. The stars are the terminal arrival waypoints and fixes, and altitude and airspeed constraints for the long final approach. The terminal approach landing of the aircraft is going to be aligned also with the Lszh localizer, the horizontal localizer and the vertical glide slope that receives the radio frequency transmitted from the threshold antennas of the runways that we have for landing and for takeoff. The runway 14, and it has been is having a separate radio frequency for its runway that we use in either airport, and also heading we need to have 136 degrees for the runway 14. So we're gonna be having a line with the horizontal localizer, also the glide slope, the vertical flight path for approach. We're gonna be having 35-30 degrees of flaps for approach and landing, about 60-70% of engine thrust, and also airspeed about 170-180 knots. We're gonna be having also the line gear extended and the pitch attitude like 90 degrees. So let's get into the complete flight. So I'm gonna use the flight management computer here, also the inputs from the mouse pad over here. As you can see, we have the mouse pad for the flight management computer and the keyboard over here. So I'm having my own over here, my own mouse for controlling, and also the computer for controlling the aircraft flight management computer. So gonna input the data here. So you're gonna see we're gonna input here the data from the flight management computer from the mouse pad like this. We can use either mode, so we can use like the route over here. We can use the index over here. So we have identity, position, performance over here, takeoff, approach, announce seat status over here. As you can see, navigation data, flight plan, load traffic control, load route, save plan, save flight plan. You can use also from these buttons over here, the keyboard control. So we go over here from this view of the cockpit to set up the flight management computer, the control quadrant. As you can see, again we have the mouse pad and the flight management computer, this nice view of the cockpit. So we're gonna set up over here. We can set the identity of the aircraft. It's Boeing 787-900, the NX engines and the rack cycle, the position. I'm gonna set Lszh airport, the international airport in Switzerland. Over here, so we said reference airport, clear over here. So it's gonna give us the inertial coordinates for alignment, the longitude and the latitude of the aircraft. Performance, we can set 0 fuel weight plus fuel on board. We're gonna have the gross weight for takeoff, cruising altitude, cost index, fuel freezing temperature, cruising center of gravity, and the reserve fuel. For flight, we're gonna set the route first, Lszh airport origin, and this is departure and destination, arrival over here. Copy paste. So we clear over here, and we use runway 14 over here. So we have departures over here. We can set either runway for departure, runway 10, runway 14 over here, runway 16, 2832, and also the stars, the seats that are instrument departure waypoints and fixes. So we set runway 14 and Zulu to Alpha. So this is the departure, and we set the arrivals. We can set arrival either runway 16, 28, 34, ILS 14, ILS 16, ILS 28, ILS 34, ILS GLS 14 localizer over here, 28 localizer 34. So we're gonna set ILS 14 Trans Amity. The stars is gonna be the solar terminal waypoints and fixes, Negra 1 Alpha. So we have the legs set over here. You can see the route is displayed with blue, the heading, the first waypoint, second, third, fourth, Zurich, the distance from its waypoint, climb to the cruise level, cancel the discontinuity, then descend, Zurich 701 701 TRA CI14 Osnem runway 14. So in order to activate the route, we have 0 fuel weight 332.7 thousand pounds, plus fuel on board 33.9 thousand, gross weight 356,000 pounds, reserve fuel 5%, and the cruise altitude 25,300 feet. The cost index 100% over here. Fuel freezing temperature minus 37 degrees, and the cost index 38%. Execute destination format. So we have the legs activated now. The first waypoint over here, 136 heading, 2 nautical miles from the runway, 250 knots, 1900. Then the second one, we make left turn from the runway, 250 knots. Third one, 3 nautical miles, 5 nautical miles. Left turn 052 Zui, 6 nautical miles, 301 knots, 6000 alpha. Then next waypoint, we make left turn 071, 26 nautical miles, 301 knots, flight level 22,200. Then we make a right turn 230 degrees, 12 nautical miles from Negria, 320 knots, 11,800. Then we descend from the Matif 12 nautical miles to the Amiki, 6 nautical miles, 258, 9 knots, 10,400. Zui 9 nautical miles from Amiki, 180 knots, 7,000 alpha, 276 degrees, 290 degrees, ZH 701, 6 nautical miles from Zurich, 180 knots, 6,000 alpha. Here is the stars, start the terminal approach and landing, approach for landing here. TRA 180 knots, 5,000 alpha, 290 degrees, CI 146 nautical miles from TRA, 184,000 alpha. Then we make a left turn 5 nautical miles from the previous waypoint, 4,000 feet and 170 knots. Then 8 nautical miles from Osnem, it's the runway 14, 114 knots, 1,430, and the takeoff go around. So this is the complete flight plan for the aircraft, or route or flight path. Also foot flaps for takeoff, center of gravity 23%, and takeoff speed V1, V8 and V2. We have also other factors, departure, alternate, VNAV, progress, hold over here, fix, and navigation radio. So we set here virtual cockpit. We need to set the engines to make an engine start demonstration. So we're gonna set the engines over here. We have the left and the right IDZ, the grid charge generator, 180 to 100 volt, 400 Hz frequency, the battery, primary flight control computers in the auto position over here, heading reference over here, the data computer. We have the flight control over here, surfaces, also battery, test down power on, FD door, passenger oxygen over here, window heat, runner turbine, the hydraulics. We can set the hydraulic pumps, the left and right, engine driving, primary demand to the off position. You will see what happens. Then we set to the on, then back to the auto to test them. We have the electric as a backup. So we have also the recorders. We have the cargo and APU fire, the electronic engine control, normal and alternate mode, and the auto start system here. You can set both engines or either one. For start, we can set fuel jettison. We can dump some fuel in flight and arm the nozzles and how much fuel to remain to make an emergency landing with less weight. Also, we have the fuel booster pumps here. You can see the left and the right wing fuel pumps here. The booster pump, the crossfit valve is off, but we turn it on. You can feed either engine with other pump or either tank and balance the fuel between the left and the right wing. So this is the fuel booster pumps and the crossfit valves and the balance. We have the wing and engine on the ice over here, so we can set auto or on. We have also the bleeder for cabin pressurization, oxygen regulation, hydraulic fluid tanks over here, pressurization, and cabin pressurization, and wing and engine on the ice, hot air. So we need cabin pressurization here. In the manual mode, we use the outflow valves for climb and descent, open and close. So we use in the auto, we need nothing to do in the automatic mode. So we need to start, make an engine start demonstration in a couple of minutes. So you will see how we're gonna make it. We have a few things to see over here before going the engine start demonstration. Last thing, the autopilot set over here. So we have the autopilot flight director, LNAV and VNAV right now function. You can see we turn on and off. It will display. We turn the flight director over here off. It will disarm the system, so we have it on. The auto throttle left and right also on and off. Disarm the autopilot, disengage this slider, so we can use also the airspeed here as much as we need. So I'm gonna set 253. Flight level change, climb continues. Other modes are bank angle, limit, and flight. I'm gonna set the heading over here 136 degrees heading for the magnetic north pole heading of the runway. We're gonna use for takeoff, for landing. Altitude we can set over here. So I'm gonna set like as many thousand feet as we need. So we're gonna set 35,300. I'm gonna set vertical speed, flight path angle, so zeros. We can set descent like this, or a climb like this, the other way. So you see the plus sign. Now we're gonna be climbing with this rate of climb. So we set these systems here. We need to see the last thing before going the flight. The systems display over here. So whatever we see in the overhead panel, we have the hydraulics, APUs running, oxygen and liquid cooling. We have also the electric over here, left and right, IDZ 120 to 100 volts, 400 Hz frequency, the APUs running, the drive load cell, also the battery, 31 volts and the average of the battery. So this is the electric, the hydraulics. You can see where the hydraulic fluid goes with system. This hydraulic pressure. Also left and right engine driving, electric C1 and C2, shut-off valves, some emergency, and the pressure 5,100 psi each system, and the quantity of hydraulic fluid tanks, the fuel on board. So we have 11,000 left, right wings, right fuel tank, left and right wing tanks, 11,000 the center one, 11,000 total, 33,500. Low and high pressure fuel valves are open, feed both engines from the center tank or the wing tanks. The APU is fed from left wing is with this motor. The crossfeed valve is off, but if we turn it on, you can feed either engine with either pump or either tank, and also balance the fuel between the left and right wing tank. Also, you can see the minimum fuel temperature minus 37 degrees, below which the fuel is in flight, and the fuel temperature right now. So we recirculate the fuel and the oil on the lubricant. The air pressurizer from the packs, from the engine's doors are closed. The cabin can be pressurized. The gear, pressure of the tires, temperature of the brakes. Flight controls over here, you can see the deflection of all flight controls. The tail, also the rudder pedals, and the horizontal train stabilizer. So this is the last thing to check before going into flight. The flight controls. Also, IFS display over here, maintenance, circuit breakers, circuit breakers over here, and we have the checklist and the communications. So normal menu, before start, after takeoff, descent, approach and landing. So go in the navigation display again. We turn off both engines over here, as you can see. So both engines off, fuel control off. So you can see what happens. We have the amber indication, that we have the engines off. So if we look outside, you can see we have we have the engines off. There's fuel starvation from the engine, so we need to restart over here very quickly. Auto start, both auto start to the on position, left and right. You can see the amber and the overhead panel reconfiguration for engine start of the systems that participate. So we have the N2 is increasing. We have only pressurizer right now from the APU is admitted. So you can hear the roaring from the engines. It's only pressurizer. So we can admit now the fuel flow on left and right wing fuel tanks. Fuel flow actually to the engine. So we have the auto start here is initiating. So we have the pressure is increasing, and both pressure and fuel admitted into the engines to make combustion. So above 50%, 51. So you can see the messages are going off. So we're gonna be having running engines above 61%. both engines are running, so we can go for takeoff like this. Flaps up for takeoff, speed brakes on. So advance the thrust levers and go to the runway for takeoff. We take the air traffic control clearance over here. So we taxi over here. We take the clearance from the air traffic control. So parking brakes off, advance the thrust levers to the takeoff ground position. Over here, as you can see, full takeoff power. Align with the center line. So we have, I'm gonna press the yoke down until 100 knots. We have 80, 90. So we have 130 V1. We rotate, pitch up like 9 degrees, the aircraft. So we climb, we have the rotation, positive rate of climb over here. So landing gear up. And full takeoff power over here. So you can see we have the terrain here, red, green, yellow. Also the pitch altitude of the aircraft. You can see here we are 2,000 feet above the ground, 2,100, 200, 300, but 4,000 feet above the sea. The airspeed is 199 knots. The pitch altitude right now of the aircraft. The wind direction and speed, the vertical rate of climb 5,000 feet per minute, 20 degrees, and also the stall speed here. You can see the terrain, the flight plan. So we use less pitch altitude, and also we can use we can see the terrain around us as we're climbing. So this is the air data in the engines. Also you can see we are like 4,000 feet above the terrain, 4,000 feet. You can see the aircraft flying above the ground. The green is the terrain below you. So we need to start the turn now in a couple of seconds. So you can see where we're flying right now. Depart the runway over here and climbing over Switzerland. So we need to turn. Start the turn here. Keep climbing. So you can see we take this turn, manual turn over here, no problem at all. So 145 knots, keep climbing. From the other side also the flight plan, and we have it. So this is the view of the cockpit after takeoff over here. If we look also outside, you can see here beautiful view of the aircraft, the Boeing 787. So very beautiful view over here, as you can see as we climb the Swiss Alps and the lakes and the Boeing 787. view. So we make a small turn over here, as you can see, and we have 12 more minutes for going back to the airport. So you can see we have this intercept waypoint, the ground speed here, the wind direction speed, the range, and also you can see also the wind direction here, the airspeed 166, 67 knots, the stall speed, the other in red, indication we need to avoid the pitch altitude like 10 degrees, we climb with 2700 right now, 16,000 feet, and you can see also the aircraft symbol and the map here. Also the other side, we need to pay attention to the other side also. So we need to make a turn now, as you can see. Along with the heading, with the LNAV function over here. So very easy, we can leave the hands off from the flight controls, no problem. For the aircraft it keeps flying the way it should be, as you can see. So I'm going to be making a turn in a couple of minutes, as you can see. So this is the view from here. You can see the Germany, my homeland, the Bayern Munich in front of you, the Swiss Alps, the lakes, the galactic view, also the France in this side, and the Italy down here. So I'm gonna making the turn right now. Gonna start turning. We're going back to the airport. So you can see how we turn over here. We can use some right rudder to make more steep turn. So we overflying here this place, Bayern Munich, Germany, very close. So this is the Boeing 787, 31,000 feet overflying this place, as you can see. Hope you like it. So this is the turn and the lakes. So we have 8 more minutes to go back home. Need to align with the flight plan over here. Increase also our airspeed. So we're gonna be leveling off like 33,000 feet. So we level off here, as you can see. So we retract the flaps right now, and we need to follow this flight plan here, this route, as we fly. So we're gonna be having the chemtrails. Here they are, frozen vapors from the exhaust of the engines of the aircraft. Hope you like it. So we need to pitch down a little bit as we fly. So we leave behind the lakes, the Germany over here, the France on this side, galactic view, as you can see. So we have the beautiful galactic view over here, and we're leveling off like 25,000 feet. So we're gonna start the descent now back to the airport. So we start descending now. We have we overflying the airport over here. So increase the airspeed also and the rate of descent. Extend the speed brakes, as you can see. So we're gonna be having idle thrust in a couple of minutes for the descent over here. So here we are descending, as you can see. Keep descending and have like 6 more minutes for the landing to go. So hope you like the view of the cockpit over here from this altitude, 32,000 feet. So we need to cross through these waypoints here, as you can see. Also in this screen, next waypoint, ground speed. So we leave behind the waypoint and we go for the next one. We keep descending. We have transition altitude over here. Increase rate of descent, idle thrust. And start off for the turn now. For going into the airport. So we start the turn. Keep descending. You can see, keep descending. So this is the turn for entering the approach and landing. Use a little bit left rudder here, as you can see. Keep descending. And also keep turning. We need to turn on time. We need to turn like 60 more degrees. Also we have here, cross this altitude, we're still way too high for the approach. Keep descending over here. So going to be aligned with the heading over here of the runway. So we are aligned with the runway heading. We can let the landing gear down, as you can see. So keep approaching. Also some flaps over here. So keep descending. Need to add some flaps maybe. When adding some flaps. So we have 2 more minutes, I believe, for the video to end over here. So we're gonna have the outside view for landing like this. So we need a few more minutes to go for landing. We have some side wind, some wind gusts over here. So we need to align with the wind gusts and the side wind. Also use a little bit more flaps now. And we have 1 more minute for the approach and landing over here. For this part also you can see the Lszh localizer, the instrument landing system. We need to follow over here the Lszh localizer. So we are inside the localizer for approach and landing. Also inside the glide slope, as you can monitor, you can see the runway in front of us and our airspeed here, the altitude above the ground, and the head-up display. So we need a few more seconds to go into the runway. The video will end in 50 seconds approximately, so we need to land faster than the video ends. I don't have more record time for this video, unfortunately. So we use idle thrust here for approach for the touchdown. So we're leveling off for the flare over here. As you can see, we haven't got the flare. So this is flare, touchdown, beautiful touchdown. Parking brakes set and thrust reverse. So we use a full thrust reverse over here with the parking brakes. You can see thrust reverse. So we're slowing down